tell us about why the center was created and what actually goes on within the halls and walls of the facility.
Okay, so the center was driven by the vision of one person, Ted Rappaport. We did have an existing wireless center, but it was kind of diffuse. Its activities were fairly diffuse, multiple objectives. And he proposed that we focus, at least initially, on one area, and that is what technologies will succeed the current fourth generation cellular. And so, his vision was in the fifth generation, given the bandwidth requirements, given the latency requirements that we would like for fifth generation wireless, we cannot continue using the existing spectrum but have to move to the millimeter waves. These are the waves beyond 30 gigahertz. And they are relatively unused, unlike the very crowded spectrum we have among current users.
Right.
And this spectrum, of course, is considered the best spectrum, the one we currently use, because it penetrates through walls. It is very good coverage. And for that reason, it is sought after. It's now become very expensive and would not be available the amount of bandwidth will not be available that we need for these new applications. So he said, let's focus on millimeter wave and see what its constraints are, how to get around the constraints of millimeter wave, because these are some of the myths associated with millimeter wave.
Sure.
That it's a poor...
propagation is not very good.
Propagation
Distance is not so great.
Right. And so he's... So this is the perception, and to some extent the perception is true, but given how fifth generation will operate, it will essentially circumvent many of those constraints. And once we proposed that, and I must say other companies were also looking in that direction, many companies got interested in joining with us, and we now have 14 companies which have joined the center as its members to push this as one of the central core ideas for this center.
Millimeter wave.
Millimeter wave.
As the evolution beyond 4G, moving to 5G, millimeter wave is at the core of this, your philosophy and vision.
That's right.
Okay. And then what goes on here? What are all the students doing? I know we're here in the summertime, so it's quiet, but during session, what are you doing? What are the students doing?
So we are still fairly active given it's summer. We are, because a lot of the research gets done in the summer because there are no distractions of classes and committees and so on in academia, is to look across the protocol layers of a 5G system, from propagation right up to applications, and attack each of these layers and see what would change in a fifth generation system.
Okay.
So we have people looking clearly at propagation, because summer is a good time to do outdoor propagation studies.
Right.
So that is going on. Several of TED students are working on that. At the medium access control layer, which is the next layer on top of the physical layer, there needs to be some innovation there as well. Because to get the kind of range that you need in millimeter waves, you have to have a focused beam pointing at the user. You cannot use an omnidirectional antenna as in 4G. So if you're using a focused beam, then you have to, in a mobile environment specifically, you have to identify where the user is. The user has to identify where the closest base station is. So you need to essentially lock in between the base station and the user. So this is a non-trivial task, because you're moving, the best base station may change over time as you're walking or driving, and this is very radically different from what 4G does. So here we have students looking at what is the time to lock in, what is the best way to set up the frame structure to allow for this lock-in, what happens if you lose connectivity, how do you get alternate connectivity, is a very exciting area, I think, associated with this technological constraint of millimeter waves.
Over the past year, RCR Wireless has been around the world at many conferences, and it seems as though the word 5G, or the acronym 5G, is just continuing to gain momentum in two areas, Internet of Things, but more importantly around connected cars. Vehicle to vehicle, vehicle to infrastructure. Where do you see millimeter wave fitting into the car equation?
The car equation has a couple of features comparable to the operating theater environment I just mentioned. One is very low latency because you need very fast reaction times if you're going to hit something in your car or avoid some obstacle. And it needs to be very, very reliable. You're not going to give up control of at least some aspects of driving your car unless you're really, really sure about it.
Right.
So I think these are these are big challenges for connectivity between cars and cars to infrastructure that need to be addressed. And we hope that with millimeter waves and other technologies, we could address that.
Do you think you'll address the latency issue at the MAC layer, at the radio layer? Where do you think, or is it a combination of all of the above?
So the latency numbers people are throwing around are really, really challenging. They're talking about a couple of milliseconds.
Right.
So if you just take
by 2018, I think.
2018, right. So if you do the math, I mean, a couple of milliseconds, even at the speed of light, doesn't get you very far, okay? And if you add in the processing time and the fact that you're not going at the speed of light in some cases, this means really you would have to move a lot of the applications and application servers closer to the user. So you would have to put servers very close to the base station, perhaps use some concepts of fog computing. This is a variation of cloud computing where the computation, instead of being in some giant center in Utah or somewhere, it would be perhaps even on your base station. And that's the only way I know of to reduce latencies is to reduce the round trip time to wherever you need to go.
Yeah, no, I was in Barcelona for Mobile World Congress, and the HetNet guru now at Oracle made a bold pronouncement that he felt like the blade servers were going to be right there at the base stations for this very issue. So you got this notion of cloud,
right,
at the same time decentralized computing at the base station. So how do you reconcile those two? And is that something that the Wireless Center is looking at? So
we are discussing it. I don't think we are focused on it. It's clearly this this notion of a fog which is a cloud close to close to the ground has to be done. Now if you look back, and why was cloud computing so popular was this need to aggregate and therefore lower the cost of computing, right? That was one of the drivers.
Right.
And the management of those machines. If you now again distribute it, this is like the pendulum is swinging back to the days of desktop, standalone computers almost. I wouldn't put it that strongly, but it's certainly a move in that direction of putting computing closer to the user again. So, but I think given the knowledge we have gained about how to manage cloud computing, if we can make it cheaper, smaller, closer to the user, we can use some of those lessons to make this happen.
Okay. Yeah. Well, we're going to take a tour of the facility, but before we take off, when you give someone a tour, what are the major stopping points along the NYU Wireless Tour? Okay,
so I can give you what we would have done if we had done the full tour. Yeah. So we essentially follow the classic layer model in our tour. So we start with the propagation, the physics of it, what happens with millimeter waves if they hit a wall, and we show the equipment that measures the strength of the signal.
Right.
We have some very sophisticated equipment to do that, so it's always neat to show that.
And then you can test multiple bands, multiple spectrum bands at different densities of wall, et cetera.
Yes.
Okay.
So we do both indoor measurements, which to see what happens. We go through drywall versus brick, et cetera. Okay. Windows, and also outdoor measurements, which is fun because if you do it in New York City, you get the full urban version of what will happen with its particular environment. Then we move on up the protocol stack to the MAC layer work that I mentioned with focused beams. And we do have National Instruments PXI piece of equipment in which you can emulate the higher layers of the protocol stack in real time. So it has the computational power to do that.
Is that LabVIEW, using their LabVIEW product?
Using the LabVIEW product. So students are working on that to essentially have all the key elements of the protocol stack implemented in there. We also then move on to the application layer. So we show them some of the video applications, which, as you know, use more than half the bandwidth of the internet today.
Right.
So we are working on those aspects as well. So that's, broadly speaking, our tour.
Okay.
Yeah.
Well, good. Well, let's check out one of your classrooms, and
Sure.
we'll talk a little bit about the Brooklyn 5G Summit there.
Very good.